Great, and hello to everyone who watches in the recording. So today, what we're going to do is go towards the first family of optimization problems that we are going to encounter in the course. Arguably, before this lecture, we already have seen quadratic programs. We already have seen them. And as we go along, you would see, you would see shadows of those every now and then. Remember, quadratic programs, that is least squares with inequality constraints. Okay, in a sense, you can say that is what quadratic programs are. Okay. Now, this lecture we are going to talk about linear programs. Remember, before we also discovered that convex optimization we can define in two ways. One is problem with convex cost function, convex domain. That would be a convex problem. Okay, that is one definition. Another definition using Boyd's idea of disciplined convex optimization. That is, convex optimization is a problem constructed from convex blocks, such as, for example, quadratic cost function, linear constraints, etc. So from specific blocks which are recognizably convex. Okay. So it is not enough for the region, for example, for the domain to be convex. It also should be recognizably convex, as in it should be one of the building blocks that we are allowed to use. So those are two ideas. And today we are going to see this family of programs. And we are going to pay attention at the convexity of domains, convexity of cost functions. Notice how they play a role. All right, so let's begin. So first, linear programs are programs of this type. We minimize cost function which is linear with respect to decision variable. Decision variable here x. Okay, so this is a decision variable x. The constraints that are allowed are linear inequality constraints. Sorry about that. Linear inequality constraints and linear equality constraints. So two types are allowed: linear inequalities and linear equalities. Now that you have seen our lecture on H representation, you can recognize that what we discuss here in terms of, let's say, linear inequalities, that is just a polytope, right? Convex polytope. So something like this. Something this shape that would be can be defined with linear inequalities. And what, of course, you mean when you say this? So this means interior of this polytope. Okay, I'm not going to try to be too pretty here, but that's the idea. The interior of this polytope. All right. Now, let's before we move on, let's ask ourselves, what does this mean? What does this mean? Well, this is a linear equality. So it means that this describes, or linear equalities in general describe hyperplanes. Okay, hyperplanes. If D was equal to 0, it would describe a linear space. Okay, linear space. But if D is not 0, it means there's an offset from the origin. So it is a hyperplane. Basically, it just is something like a plane, but the dimensionality of the plane is depends on C, on the null space of C, and the dimensionality of the space in which the plane operates depends on the dimensionality of X. So if X is like 4-dimensional and null space of C is 2-dimensional, it will be a 2D plane in 4-dimensional space, for example. I'm doing this a little bit off the top of my head, so please don't mind if I make a mistake computing dimensions somewhere. All right. So this is a hyperplane. How can it look in practice? Well, in practice, the way it can look is something like this, for example. Oops, let me can change. Something like this, for example. So what I draw here, this line, will be a one-dimensional hyperplane in two-dimensional space. So that would mean that our actual domain in this problem would only be this part. Okay. So while we had all this pretty polytope, since it was intersected by this hyperplane, we only have this what do you call it? This segment, line segment. That is the only thing that actually determines the domain. Okay, so this is how we work with domain here. So it's the intersection of this hyperplane and this polytope. Notice also that a lot of those inequalities become useless. You can actually represent this whole domain much simpler than what I represented here. And indeed, this is a very typical case. And often solvers will try to minimize the number of constraints before solving a problem. There are procedures to get rid of useless constraints. And solvers often do that. So here it is much easier to simplify this problem by considering only two constraints that prevent it from going over here and over here. So just do two inequalities, and that will be sufficient. All the rest of inequalities are not really needed here. And that is possible to do. So this is typical. Don't think of it as like, oh, this is strange. No, this is completely normal. But often this is done automatically. So this is not something that you have to do. But if you want your program to run fast and your constraints, you know them in advance, and you can simplify it this way, that is a great idea. In general, for example, if your cost function, let's say, varies, but your constraints stay the same, great idea to simplify it before putting it into the optimization, because this would save you time. Usually, though, in practice, we don't know constraints in advance, so simplifying it in advance would be difficult. So solvers often do it in real time. So they often simplify before solving the problem. Yeah, so at least that is kind of done as pre-solve, what we call. All right. Now the solution is the cost function is linear, as we said. Okay, this cost function is linear. So let's pay attention to it for a second. So this is a cost function. It is linear. What does it mean? Well, it means that we would have a direction in which it increases the fastest. So there would be some kind of a direction. Let's say the direction in this case, for example, this way, where the function increases as fast as possible. So in other directions, let's say in those directions, it also increases, but not as fast. Okay. And let's say in this direction, it decreases, and maybe in this direction, it actually decreases as fast as possible. Because it is linear, right? If it was quadratic, you could say it increases in this direction, this direction, depends. It increases the further you go, the faster it increases, blah, blah. You understand how parabolas work, right? The slope gets higher and higher the further away you are from the origin. For linear functions, none of this is true. The slope is always f. There's a direction in which it increases the fastest. And this direction, by the way, is very easy to understand what the direction is. It is f. That's it. It's just f. Because if f and x are collinear, they're going to have the maximum dot product. If they are orthogonal, they're going to have zero dot product. If they are collinear but look at the different directions, it will be the smallest dot product. It will be the same as here but negative. Okay, so the cost function will increase fastest in the direction of f. Okay, that is what's going to happen here. Now, all of this is kind of fun, looks very impressive, etc. But what does it teach us in terms of practice? Well, what it teaches us is that we can actually geometrically find the solution here. Well, the solution will be in this direction, right? Roughly in this direction. But we can only go along this guy. So where along this guy the solution will be? Well, I would argue it will be here. Let me make it small. It will be here. That is where the solution will be. Because if we go anywhere down, like to the southwest direction along this segment, we're going against the direction of this vector. So our projection onto this vector would increase while we go to the northeast. Okay, so here. Okay. Great. So we can just look at it. We can already find the solution. What is very important here is that a solution cannot lie in the interior of the domain. Cannot lie in the interior of the domain. Why? Well, imagine if this was a solution. Okay. But then there is the domain, as long as it is not trivial. So as long as it doesn't have, it has more than one point. It would you can vary your position slightly, and if you vary your position in the direction which is slightly like it has a positive dot product in the direction which has positive dot product with f, your solution would actually oh, sorry, the solution in this case, of course, is this one, right? Because this is maximum, we are looking for minimum. My apologies. This is minimize problem. Okay, so this is the solution, of course. All right, so if we shift our motion from like this middle point slightly, let's say to this direction, slightly, and the dot product within the solution, within the current, within the direction in which we shift, and f is negative, then the solution will decrease, of course, right? If you want it to be written out, I can say write it as this: x plus delta x. Here I did not. This is, you can read it as delta x, all right? So if delta, this guy would be less than f times x if f times delta x is negative. That sounds kind of obvious because all I did is just open the brackets here. But as long as it is possible to pick such a delta x that dot product between f and delta x would be negative, we can always improve our solution. So there are only two scenarios. One scenario is all delta x that are possible are orthogonal to D, which would, geometrically speaking, imply that our domain looks something like this. So our domain looks something like this, whereas our direction of decrease looks something like this. Okay. So in this case, all solutions have the exact same value. We don't have any preference, so we can pick anything. That is scenario number one. And scenario number two is that our domain is, just something, what we would expect. It won't be orthogonal to, like a line orthogonal to the direction of decrease. Okay, and in this case, the solution would lie on the boundary. Okay, in this case, solution would lie on the boundary, because as long as we're on the boundary, we cannot pick any delta x which would further go away, because we are at the boundary. So we cannot do plus delta x. We can only put minus delta x. All right. So solution can only lie on the boundary. That is what I was trying to say. And if this is somehow not convincing, you can go ahead and just try to do it geometrically. you understand that you linearly increase in certain direction. Try to convince yourself that it is impossible to find a solution which would not lie on the boundary for this problem. Questions so far? All right. If you have questions, just unmute and talk. Let me double check that everything. Yep, that's not okay. That's okay. Let me know if I'm too quiet or something, because my microphone for some reason doesn't show me as a volume. So was I too quiet?
Yeah, it's okay.
Oh, it's okay. Okay, good. Usually I have an indicator, but today for some reason it doesn't. All right, good. Good. Okay. Next. So let us demonstrate a few problems which wouldn't have solutions. So for example, this problem right here wouldn't have a solution. Why? Well, because it can infinitely decrease in the direction minus 1, minus 1. So as long if we can pick x1, x2 to be equal to minus 1, minus 1, minus 2, minus 2, minus 3, minus 3, minus 100, minus 100, etc. Infinite decrease. So it doesn't have a solution. A solution, remember, is a finite number. So it doesn't have a solution. Solutions are on the boundary, and this problem, as you can see, doesn't have a boundary. That is a specific property of LPs. LPs solutions always are on the boundary. So if you see LP without boundaries, you can instantly assume it isn't going to have a solution. Good. Here's another example. This one has a boundary, but the boundary does not bind us, prevents us from going where we say we are going to go. So this boundary here, let's study it. This is a boundary. What it says is that x1, so x1 is less than 1. Okay. Well, we decrease in the direction minus 1, minus 1. So picking x1 less than 1 is actually very easy. So it doesn't prevent us from doing anything. In fact, even if it was bigger than 1, it still wouldn't prevent us from anything, because we could always pick x2 to decrease. And we would still decrease infinitely. Just to illustrate, let me draw it for you. Let me draw it for you. So we would have let me show it like this. We'll have something like the direction in which we decrease. I would again show it with an arrow. Is minus 1, minus 1, this direction. In this direction, we decrease. Okay. So if our boundary was x1, so here our boundary is x1 is less than 1. Okay. So it means that prohibited region is x1 bigger than 1. Okay. So this is the region that's prohibited. Clearly, we did not prohibit our infinite decrease to into this direction. Okay. Let's say we say x1 is bigger than 1. Okay. That would mean this whole region is prohibited. Well, you would say, okay, this looks as if we prevented infinite decline, right? But we didn't. Actually, our direction would just go this way. So we can always have a smaller and smaller cost function by going this way. So what would we have to do to prevent this decrease is, for example, by having something like x1 bigger than 1, x2 bigger than 1, for example. That would be this intersection. And then you can instantly say that the solution would have been this part here. In fact, it is the only vertex in this domain, and it would be the solution. So This is this is how we could have made this into something with a solution. Questions? Great. Let me now show you.
I have one question.
Go ahead. Go ahead, please.
On this drawing, we have a big red vector. How we draw it? A bit little, maybe.
Come again?
We have this big red vector. How
Yes.
we receive it?
I
see 1 and 1, and I don't understand why we draw it in -1, -1.
Okay. So we want to minimize, right?
Yeah.
So this function will increase in the direction 1, 1, right? Increase in the direction 1, 1. So roughly speaking, in this direction, it would increase. Now it is a linear function, so it would decrease in the opposite direction, right?
Okay.
Yeah.
Now I understand.
Yeah. Okay. We can also say that it would decrease in the direction -1, -1, because the dot product between -1, between that and that would be the smallest. Okay. Good question. Good question. All right. So now let us move on. Now I will show you something. What I'm going to show you now are a few examples of how to use linear programming to solve problems which look nothing like linear programs. The whole course of convex optimization is going to aim at giving you ways to use those few tools which are explicitly given to you, like QPs, LPs, least squares, etc. You'll see a lot more. How to use them to solve problems which look nothing like those problems. In fact, our goal will be to learn how to transform problems into ways, into something that looks like LP, QP, etc. So that is kind of like the beauty and the mastery of the convex optimization, being able to transform one problem into another. Okay, so here is a function. We call it convex piecewise linear function. Convex piecewise linear function. The function is defined like this. It is a max over I, so it should be stating here over I of AI times X plus BI. And this thing is a convex function. So how does it look? Well, here is the example below. Let me illustrate how we can think about it. So first, there are three functions three functions that are given here. Okay, those A, I, X plus BI. So those are linear functions. Essentially, those are lines, right? Here, yeah. So those are lines. In the 2D case, in the 1D case, where X is scalar and A is scalar, they just become line equation, normal line equation. In a high-dimensional case, this would be hyperplanes, but let's stick to 1D case for now. So those are the three functions that we have, okay? Those are the three functions that we have. Let's consider how do we get f of x. Well, f of x is the max over all three. So let's consider, for example, the value of f of x here. How do we get it? How do we get this value of f of x? Well, we can draw all three lines. So here's the first line. That is a1x plus b1. Here's the second line, a2x plus b2. Here's the third line, that is a3x plus b3. Okay. So 3 lines we draw them. Now, we want to find the max over those lines at this particular point. Like here, we want to find the max. So the values that those functions attain at this junction this is one value, this is another value, and the third value is somewhere downstairs for this line. Okay. So you can clearly see that the winner is this guy. So this is the winner. Let us consider the value here. Oops. The value here, let's see. Okay, so we have, again, 3 values that the function attains. That is a2x plus b. And here is a1x plus b1. And here is a3x plus b3. Again, we clearly have a winner. The maximum value is this guy. Okay. Last example. Let us consider the value of the function here. Well, again, we have our 3 lines have 3 different values. So line number 2 has a value here. Line number 3 has a value here. Line number 1 has a value somewhere downstairs. Again, we have a clear winner. So the value that the function will attain is this guy. So you can see that this max over 3 lines naturally gives us this shape. What shape? Well, let me draw it in bold. Well, this shape, right? Oops. This shape. Okay. So this is what we get. This bold outline. And it is going to be convex. I'm not going to prove it to you, but you can, if you want, you can prove it to yourself. That is actually quite interesting, trying to prove that this function is actually a convex function. But you can see visually it looks convex. Visually it looks convex. Okay, okay. So this also looks like a linear approximation of a parabola, right? It doesn't have to be a parabola. So the shapes this function can attain are all linear shapes that such functions can possibly attain. So it's so let me make it less bold. And here coordinate axis. So I'll just try to demonstrate the possibilities, how it can look. For example, it can look something like this. Let's say something like this, then something like this, and something like this. That is possible shape. You can see it is not quite parabola, it is skewed to the side, okay? Another possibility is that it would look like this. So triangle, kind of like a triangle. Another possibility, it would look like this. So kind of like trapezoid. Okay. What is impossible is something like this. This is impossible. Why? Because this is not convex, and we said it is convex. And in fact, why it is impossible? Because this guy here would clearly dominate this line here, would have clearly dominated those lines. So the final shape would have been, if we added this line here, the final shape would have been like this. Some other color. The final shape would have been something like this. Right. So this would have been the final shape if we had this line here. All right. Okay. So what I'm trying to say is that this is somehow a linear approximation of something convex, and it can be as precise as you want. So as long as you can use it, suddenly we can work with pretty much any function that you like. Let's say you wanted, and I'll do the white screen again. Let's say you wanted to use like half a parabola. You didn't want the parabola, you wanted half a parabola. So you wanted a function that looked kind of like this, and the other shape is a parabola. It's impossible to, I mean, it was possible to do it before, of course. Of course it's possible, right? But it's slightly difficult. So you can approximate it like this with lines. You can see it roughly looks like a parabola. So, is a good function, allows you to create non-symmetrical functions, allows you to approximate. We can use this function in a linear programming. So we can find the minimum of this function as part of linear programming. And that is the interesting situation. We could find a linear program which would solve the minimization of this function. Do any of you have an idea how to do it? And do you have questions about geometry of this function so far? If something like this is not clear, ask questions. We're going to, next few slides, we're going to continue working on it. So. Okay, assume it is clear. I assume it is clear. Let's see how we can minimize this function. So the problem is to minimize over x this function. This is a problem. Minimize over x this function. This can be equivalently transformed into the following LP. You minimize t. Okay, you minimize t. Subject to a new constraint. Subject to a new constraint. Where, let me show it like this. Where this old part here is less than or equal to t. T is a new decision variable. So before decision variables were x, now it is x and t. T would be equal to the minimum of this function. Okay. So t would be the minimum of this function. And minimizing t would give you the same result as minimizing this. Now, why is t going to be minimum of this function? Well, notice that t is going to have to be bigger than each of those, guys. So t has to be bigger than all of those lines. T has to stay on top of those lines. It cannot be below any of those lines, okay? And it is minimized. So let's go back a page and consider what's going to happen. So t is a scalar. It only determines, you can think about it as height here. So where is t going to be? T, you can think of t, if you want, as this vertical axis. So let me even draw it for you here. So t would be this vertical axis. Okay. So t, can be, let's say, when t can be like here, like anywhere on this axis, right? But we cannot just find t. That would not be sufficient. We also have to find x, which corresponds to this t. Why? Well, for example, let's say we decide that x would be equal to 1. So here. Well, in this case, t can be anything from infinity plus infinity to this value. It cannot go below this value. Why? Well, because there is a line here, this line, that goes here, and t cannot be under the line. We have a constraint saying that t is bigger than a2x plus b2. And since we chose x to be here, we cannot possibly choose t to be below this line. Okay, below this value. Okay. Now, what if we chose x to be equal to, let's say, I don't know, 10 here, for example? Well, then if it is, let's say, I'll put it bold, 10 here. Well, if it is 10 there, let's put the line vertically. I don't know if such thin lines are even visible for you. Okay, so vertical. So here is what happens. T cannot go down lower than this value. Why? Well, because T has a condition that it is bigger than x3, a3x plus b3. So it can't be below this. It cannot be below this as well, but it is irrelevant because this guy is higher at this particular x. So what you see is that the condition that t is bigger than a1x plus b1, a2x plus b2, a3x plus b3 automatically makes t to only be possible on the like to be higher than this graph. So t can be anything, but it has to be higher than this piecewise linear function. But we minimize t. Okay, we don't care what x will be, but we want the condition is to minimize t. And what is out of all possible t's? What is the smallest t that is to find here? Well, this is the smallest one. Like this is the smallest one. You can see everything else is kind of a little bit higher, right? This is the smallest one. And this is what the solver will find. It will look for such x that allows it to get us the smallest t possible. And while you find this value, and you automatically find x. Okay, you automatically find x. What is the x corresponding to this problem? Well, this x. Okay, and this would be the solution. So this would be actual solution. Right. So what happens? The solution to the problem is this. This is the x that delivers the minimum to this function. This is the actual minimum of this function. So this is the minimum. This is the x. Okay. So this is what's going to happen. And that is why this problem would actually solve this problem. Okay. They don't look very similar. Here we minimize max over ax plus by. Max is not part of any eigen. What is max? Where did we get it? But we solve this problem, which is clearly LP, linear cost, linear constraints, two decision variables. That's it. It would work the same way in higher dimensions. So, do you have questions about it so far? Okay, I'll move on then. But notice this is a very useful thing to use. You can approximate things in high dimensions as well, like paraboloids, other shapes. If you have a cost function that you want to approximate, you can use this trick. And you would get an approximate solution, but it will be a solution. And LPs are very fast, so you don't lose anything by using this approximation. Of course, the number of constraints can go very high. Okay. Now, sum of two piecewise linear functions, it can be written this way. So it is the max over the first one plus max over the second one. So that's how you sum them. Kind of feels natural. This can be represented as the following LP. So you get sum of T1 and T2, those solutions to two. The first one, solution to the second one. And for each of those, you get their own constraints. That's it. So you can even do summations over two linear functions, no problem. Okay. Here is how you write it in Matlab. I'm showing it in Matlab just to show you like a different type of code, but of course you can work in Python. So here, what I'm trying to do is I want to approximate t squared by piecewise linear function. I want to approximate at those points. So those are the points where it's going to be exactly equal to t squared. This is the derivative of my function. This is 5, so 5 approximation points. And we create those A and B arrays. All right. Now, from 1 to 5, we go to each approximation point becomes t. So t would be this and this and this and this and this. A of I becomes a derivative. So it's the point t. So it'll be 2 times -1, 2 times minus 0.3, etc. So A would be the derivative. Now, somehow it makes sense, right? If you think about it, what I'm working with is something like the function. And I want to find the linear approximation of the function. Or linear approximation, it kind of makes sense to be derivative of the function. The A part of the linear approximation will be derivative. So it makes sense. And B, you can already understand how it will be computed. It will be the value of the function at this point minus a linear approximation. So how far you have to push this function to become that. We could have written it differently. We could have written it via like A times t minus t0, etc. So there, we could have done it differently, but our classical way to describe those. So what I said just now is that we could have written it just. So this would have been possible, right? And what that would have done is simplified a little bit this guy. So B would then be just equal to, would have just been B equal to that, if I remember correctly. But this would have been a slightly different way of describing piecewise linear functions, which would work exactly the same as before, but it is just going to look different. So I stuck with the original notation, but that's also possible, of course. All right, next, what we do is we define the direction in which the function is going to decrease, which is in the direction of 1. What do I mean? Well, t is going to decrease, right? We want to minimize t. X, we don't care. So it doesn't minimize, like x is multiplied by 0. F, remember, is going to be multiplied by decision variables. In this case, t and x. Okay. Good. So linear A is A less than ax less than or equal to B. That is A. that is B in this expression. So A would be yeah, a vector of ones and A. B would be minus B. And why this is so is to get line. This is basically saying T is bigger or equal to AX minus B. So, but I don't want like T bigger than, so let me just write, you understand better. So T bigger than AX plus B, right? I don't want that. What I want is, I want to preserve less than or equal to. So I have minus T plus A less than or equal to, okay, minus B. So those two are equivalent, right? And that's what we get. That's what we get. So that's why minus y1 is a coefficient in front of t, a coefficient in front of x, minus b is here. And you call linprog. Linprog is a Matlab function. You tell it, you tell linprog, here's my cost. You tell it, here's my inequalities. And you tell it that you don't have boundaries on upper bounds on your decision variables. As far as I know, that's upper bounds. I don't remember. Oh, wait. This is not upper bounds. This is equality constraints. So you don't have equality constraints. That's it. And you, that's your LP. And that's how you solve minimization for this problem. Okay. Questions? Right. No questions so far. So second, more, I mean, I don't know, more useful, I guess, immediately. So previous one was also useful. That is the Chebyshev center of a polyhedron. So Chebyshev center of a polyhedron is defined as a point XC that is the center of the biggest inscribed ball inside the polyhedron. Okay. So the polyhedron is a polytope, just in high dimensions. We can say polytope, it's fine. And the equation describing this ball is C sub x, so the center of the ball, plus U, where U is a unit ball. Sorry, not unit ball, ball with a radius R. So U squared is less than or equal to R squared. So it can be like 3-dimensional ball, 4-dimensional ball, anything. So the question is, how do I find the center of such a polyhedron? You can imagine this is not trivial when you just look at it, right? Let me give you an example. So here's a triangle. What is the center of the biggest inscribed ball in the triangle? Where is it? How do you find it? Some of you probably have memories of high school where you would be like, okay, maybe some theorem of properties of triangles will tell me something, right? It's like biggest inscribed ball would have to have some properties. So maybe we can do something about it, right? Sure. Maybe it would work for a triangle. But if I just go a little bit more difficult, right, I would say, okay, is this skewed diamond shape? Where is the ball there? like visually speaking, it's like still quite easy to imagine how the ball would look like, right? It's like here's some ball that we can increase, right? And like visually, you can see I found the center pretty fast. But how do you do it computationally? How do you do it computationally? And with precision, of course. Well, this is also a linear program. And last year, I asked my students if anyone sees why this would be a linear problem. And one of the students actually managed to give me an explanation. If you want to try it, maybe you can, you can go ahead. If you see why finding a center of the biggest inscribed ball would be linear program, you can tell me if you see why it should be linear.
Because I have only idea.
Yes, go ahead.
Maybe we try to maximize radius, and this is our main idea. And our coordinates of this point is linear dependent, for example. Something about this, but this is just a concept. I don't know it really.
Mm-hmm. I mean, you're close to being right. Anyone else want to try? Right. So the way I would try to speak about it, and speaking about those things is difficult. I don't have good vocabulary for that either. But the way I would speak about it would be something like this: you can independently move around the center of the polygon, of the ball, and change its radius. Those things exist independently of one another, and they linearly influence penetration of the constraints. So increasing the radius of the ball will eventually penetrate one of the inequalities. Moving the ball eventually will penetrate one of the equalities. But the two do not multiply each other. So like radius of the ball shifts those points linearly, and so does the radius, a change of radius. So somehow you can do those two things independently, and that is important. That is how you get linearity. But let me just show you how it's done. Let me just show you how it's done. So first, before we do it, let me let me show you a simple problem. Consider the problem. Find the maximum of this function a times u over a unit ball. Over a ball radius r. Well, we can rewrite this. So, sub is supremum, so maximum. We can rewrite this, expanding this dot product here. So this dot product becomes a times u times cosine. So a norm of a times norm of u times cosine between them. Definition of what dot product is. Still over the same unit, ball radius r. All right. Next, what we say is a is constant, okay? A is constant. And max over u norm is r, okay? So let's kind of like show it. So a is constant here. And this thing here is just r. So this thing is just r. That is the maximum possible value this norm can attain. Okay. Oh, sorry, I managed to this thing. Maximum is r. Maximum of the cosine, on the other hand, maximum of the cosine is 1. So this is going to be 1. Okay. This is going to be 1. Okay, so let me even use a different color just to indicate. Okay, this is one. This is one. Okay, so what we got is that from this guy here, we get to this guy. Okay, we don't have u, so we don't have the red part. So this red part goes away because we don't have u anymore. How did we get here? Well, you know, I'll repeat. R is this guy. Okay, so this u norm maximum is R, so this is R. A is constant, so A doesn't need to change. A is constant, so it stays the same as before. And cosine phi is 1, so it just disappears as 1. And that's it. So the maximum over dot product on a sphere radius r would be the vector with which we have a dot product, so A, taken as a norm, times r, okay, times r. Does this make sense? Well, we'll see this idea quite a few times, so don't worry, we'll get used to it. But this is the idea. So the maximum on, I will even draw it if you allow me. So the maximum over, if you have this radius r here, this is the radius r, let's see. Maybe I can even color code it again as light blue. Okay, radius r here. And the center is this, 0, 0. So the maximum dot product that you can have, and in the direction of A. So the direction of A, I would, as usual, show it as a big green arrow. So this is the direction which dot product is taken. So the maximum that you can have is norm of A times R. And somehow, when you think about it, it starts to make perfect sense geometrically. Here is a vector u that you're going to use for this dot product. Its direction is the same as R, so directions don't do anything. Cosine is 1, and the product will be norm of A times the radius, because the radius is the norm of u. So geometrically, it's kind of clear, I think. Questions? Right. Now, oops. Now we know now this part, so we'll be able to finish the derivation. So for the ball B to be inscribed in a polygon P, where polygon P is given as all x such that ax less than or equal to b. Okay, so all x such that ax is less than or equal to b, where so this is linear inequality that defines this polygon P. Okay, so polygon P is a polytope. Okay, so yeah, it should have been polytope, not polygon. The following should hold. So AI, which is the row of A sub I transposed, should be times X. Let me denote X as a different color. So times X plus U. So here it is X. Here's X plus U. Should be less than or equal to BI. Okay. So AI is the same A as there. That is the same. The difference is that this is a matrix. This is an individual row of a matrix. So one row. Times X. Here it is just abstract X. Here we say concretely what this X is. X is X center, so the center of the ball, plus U. U is the vector inside the ball. Should be less than or equal to BI, where U lies inside this ball of radius R. Okay, so now we see that is a condition for the ball to be inside the polytope. Now notice that the largest possible value of, how do I put it, of product of AI and U, so this guy, under the condition that we saw before, under this condition, so the largest possible value of AI times U under the condition U squared less than or equal to R is R times AI. Where did we get it? Previous slide, right? So dot product, the biggest value on the unit ball is radius of the ball times the norm of AI. Okay. Okay. So this whole expression here, let me denote this one. So this whole expression here, which is the same as this expression here. So this is the same. Okay. Becomes simplified. What happens with it? Well, first, this and this become this. Okay. Second, well, this guy doesn't go away; it stays. Oh, here it is. And yeah, here we forgot this part, so what? It didn't go away. This part didn't go away. So we of course should have stayed. We forgot it here. That's it. That's it. So we managed to simplify our condition to be inside a polytope. We managed to simplify it to this final inequality. We managed to simplify it to this final inequality, which looks like this. And this final inequality, notice, is linear in decision variables. What are decision variables here? Decision variables are xc and r. A is not a decision variable. That is a polytope. In H representation of a polytope, A are rows, so half spaces. So A is given. So A norm is just a scalar. We know it. We don't. It's not a decision variable. Decision variables are xc and r. So with that, what we get is this expression. We maximize r, so we maximize the radius. Subject decision variables are r and xc, subject to the expressions that we saw previously. And that is the solution to Chebyshev center of the polynomial problem. Do we have questions? Do we have questions?
No.
Okay. Okay. So this is how we can do it. In case you wanted to find the Chebyshev center of the polynomial, now you can do it. Well, the question is, why would you want to find it? That is a good question, right? Eventually, we will be able to do the same with ellipsoids, and then it will be very useful. But even with the circle, you can say, okay, I want to stay as far away from the obstacles as possible in the region defined by polytope. Well, now you can find this space, this point, which stays as far as possible from each obstacle, if your region is defined by polytopes. So that is the solution. And since it is LP, it can be found in seconds, or in milliseconds. It's very fast. Okay, now we still have a little bit of time. Am I right? How much time do we have? Someone tell me, please.
About 25 minutes.
Okay, great. Thank you. And we'll be able to get the final part. I'll quickly show you how this one works. So let's say this is the vertices of a polytope. you can convert them this way to H representation of a polytope. This is basically me trying to get H representation from V representation in Matlab. Vert2con is not a standard library, but it is available on the internet. And similar functions are available for Python, so easy. You can get it. You don't have to write it. You can get it. Now, next is here we just get norms of each row of A. So you see, I transpose. What do I do here? I transpose A to get to make the rows into columns, and then I do vec norm, which is norms of columns of a matrix, and I get a vector. Each element of this vector is a norm of a column. So in fact, it is a norm of the original row. So those A norms that are in our cost function. Next, I define the cost. The cost is f equals to -100. What is -1? Well, it means that we want to minimize minus r. So we want to maximize r. Minimizing minus r is the same as maximizing r. I think it's clear, right? Next, what we do is we get our A matrix, which is made out of norms of A, shaped as a vertical line, concatenated with A, original A matrix. So this is concatenation. This reshape is just saying make it vertical. First dimension anything, second dimension 1. So this is how it works. And this is a concatenation with matrix A. Where does it all come from? Well, if I look, what we have here is decision variables are R and X. In front of R, we have norms of A. This is the first column of A. In front of X, we would have original A matrix. So that is the second column of A. Right. So this is why it looks like this. B is yeah, this is the this is B. I have a suspicions about spelling here. So next, what we just call linprog, and you get the center of the Chebyshev, Chebyshev center of the polyhedron as x2, x3, which is xc in our case, and r, radius of the polygon, will be x1. I apologize for the noise. It will go away in just a bit. So this is how we solve it in Matlab. You can see 14 lines, and at least those ones weren't necessary. I was just creating the problem, right? Run then, conf.how, all this was just me creating the problem. If I was given those values, we would have started from here. This would have been the first problem, the first line. Okay, good. Questions about this? Okay. Now, last one is fun. Last one is fun because it is completely mind-boggling. Previous ones at least made some sense. This one almost stops making any sense. But it is, again, something that can be solved as a LP. So there is something called linear fractional programming problem. And that is maximize this function, so this fraction over x, subject to those constraints. So maximize the fraction. Fraction is a scalar. So both sides here are scalars. This is a scalar, this is a scalar. We are maximizing the ratio between those two scalars over x while maintaining some constraints. So this is what we do. Okay. doesn't look like a linear programming at all. If you know, like if you try to plot 1 over x before, you know that 1 over x is not a function that invites linearity to your imagination. Doesn't look linear at all. So the whole problem kind of looks bizarre already. But we can make it linear. We can. So let's try. So the way to make it linear is to introduce a change of variables. So we introduce y, variable y, and we introduce variable z. Okay. What is y? Well, y would be equal to, y would be equal to x over ex plus f. What is ex plus f? That is original denominator. So let us go back for a second. Original denominator is ex plus f. Okay, ex plus f, original denominator. So y is x over the original denominator. So it is a vector variable. Okay. Now next one is z, and that is just 1 over ex plus f. And that is just the original denominator. So y, in a sense, is x over z. Okay, x times z. All right. Now, it is proposed to replace the original ax less than equal to b with this constraint, ay less than equal to zb. Okay. Fascinating, very interesting. The original one, let us just look at it. All right. It was ax less than b, aex equal to a equality x equals to b equality. So sub e. Right. So here it's proposed to replace it with this guy. So everything kind of is the same, but there is z here. Strange. Same here. So z appears in front of b. We add additional constraint that looks like this, and we say that z should be positive. Well, z should be positive. It somehow makes sense. This one makes sense. Why? If this guy can be both positive and negative, it can also be 0. And if it is 0, the denominator becomes 0 and the solution goes to infinity. So that's not something we like. We don't like solutions going to infinity. So naturally, we assume that this guy cannot go to, sorry, what am I saying? What am I saying? Sorry, I was got carried away. Got carried away. We just assume that this guy is positive. Okay. We do want this denominator to never be equal to close to 0. That is true. That is true. Now, if this guy is positive, so if z is positive, that means 1 over or divided by something is positive. So the only thing you can divide 1 by to make a positive number is a positive number. If you divide 1 by a negative number, you get a negative number outside. So this is how, since z is positive, from that we can deduce that since this is true, therefore this guy would also have to be positive. Okay, not only z is positive, but denominator is positive. And now I can say what I was saying before. We don't want the denominator to be able to go between negative and positive. If it can go from negative to positive, it can cross 0, and that is what we don't want. Okay. Okay. So somehow asking it to be positive, we already cut off all the negative part, and it can still be equal to 0 if it wants to. But that would correspond to an infinitely high solution, right? Solution that goes to infinity. All right. The only mysterious part now is this. Why do we have these guys? So this is mysterious, and this is mysterious. Everything else sort of kind of makes sense. Sorry, the cost function is also mysterious. Let's demystify the cost function. So the cost function, when we substitute this guy into here, what we get is c times x divided by this denominator, right? We get c times x divided by this denominator. When we substitute this guy into here, what we get is d divided by the same exact denominator, okay? But since denominators are the same, we can keep them and sum the part above. So c times x plus d divided by e times x plus f. But that is exactly the original function. C times x plus d divided by e times x plus f. So this works. So let's check everything else. So here's the derivation for the cost function. I will just quickly go over it one more time. So this is the cost. And here we have our y. Here we have our z. And we see that when we substitute, we get correct cost. So this is correct. Correct. Okay. Now this guy, how do we get it? We substitute again. Instead of y, we substitute our x divided by ex plus f. And instead of z, we substitute our 1 divided by ex plus f. But ex plus f is a positive number. We just argued it before. Since this is positive, it doesn't influence the sign of the inequality. So we can just multiply by a positive number, both sides, and get rid of this scalar. This is a scalar, remember, ex plus f is a scalar, and positive scalar. So we can just get rid of it, and we get our original expression back. And this is exactly the same as going to be done in the equalities. So this is it. This is how we went from ratios to LP. Right? So this guy actually solves this problem. Okay. Now I propose a challenge for you. Is an advanced challenge. So if anyone of you manages to solve it, we'll make sure you get extra points and everything. You can propose any meaningful problems related to robotics, which can be solved using linear fractional programming. Okay. Any meaningful problem related to robotics, which can be solved, which can be formulated in this way. Can be related to path planning, sensing, design, anything, control of motors, stiffness, anything, compliance, human-robot interaction, etc. If you find an example, that's all we ask for. Yeah, one of the fascinating ways the field has been developing in the recent 10 years is people from mathematical fields adjacent to robotics, computer scientists, etc., have been able to identify problems in robotics, which can be easily solved using tools that they know from their specialty. Convex optimization has been one of those. So work by Stephen Boyd, for example, whom I mention constantly. I kind of use his name, but of course there had been like hundreds of researchers behind those achievements. They have created tools for solving hundreds of robotics related problems, from path planning for walking robots, to design of control for switching systems, hybrid systems, to design of tensegrity structures, to control of robot cars, to MPC, to robust control, all of those things. And a big part of application has always been recognizing where something in the field can be solved as one of those kinds of problems. So if you only know this, as LP, chances are you're not going to see it in the wild. You walk past a problem, you say it is too hard, cannot be solved. But if you know that this is just one type of LP, but then something like this can also be solved as LP, right? Something like this can be solved as LP. If you know that something like this can be solved as LP, okay. If you know that something like this can be solved as LP, you might find something that doesn't look like LP, but actually is, and you can propose a much faster way to solve it as opposed to what people thought before. Is one of the ways how the field has been developing. That is just examples from convex optimization. Similar stuff happens with machine learning. Similar stuff had been going on with control theory. A little bit of this went on with group theory and smooth manifolds and so on. There have been moments where people from adjacent fields, mathematicians, control theorists, people from optimization, just brought us wonderful tools which allowed us to solve new types of problems that haven't been solved before. So for you as a specialist, that might be one of the ways you excel in the field, but being able to find tools which solve problems that haven't been solved before. So I propose you take this exercise, at least slightly seriously. Of course, there is no, this is an open question. That is not something I know the answer for too, right? Maybe there are no linear fractional problems. So it's okay. If we don't find, it's okay. But thinking about it this way is a good exercise. And I promise you, if you're going to do the same for QP, you will find plenty of problems that can be solved. With a QP, yeah. So that is stepping slightly out of the classroom and straight into research. Because that's a lot of the research is exactly that, finding what can be solved as a convex optimization. All right, I think that is it for today. Thank you for sticking with me until the end of the lecture, and sorry if we went over time. Do you have any questions? All right. Then that's it from me. Thank you, guys. We'll see each other on Thursday then. Bye-bye.